Good morning, students. In the earlier sessions on this chapter, continuity and differentiability, we have learnt about the definition of continuity, and then using the definition we have worked out problems here. We don't have any derivation in this particular topic. In today's session also, I am going to work out some problems in which I just want to discuss the continuity of certain type of function. I told in the previous session that I will be discussing the trigonometric function here. Now the first problem is discuss the continuity of the sine function. It is discuss the continuity of the sine function. Now this particular problem has been asked in the earlier examination for a 3-mark question. Now first let me take it as let y be equal to sine x. Let y be equal to sine x, or we usually write it as fx, isn't it, to denote the function. Y is equal to fx we write, or let me write it as fx equal to sine x. Now this is the one which for which we have to find out whether it is continuous or not. Now let us look at this function, sine function. As you know that the sine function is defined for all the real values of x. What do you mean by that one? X can take any real value. It can be positive, it can be negative, it can take the value 0 also. So whatever may be the value of x here, the function sine x we can define, and you remember, you have to remember an important information. For any value of theta, the value of sine theta always lies between -1 and +1. It's a fixed, any quantity between -1 and +1 are a finite quantity, I can say. That means that x is defined for all the real values. The function sine x is defined. Now let me take the usual procedure. When a particular point is not given, we take a general value. Let us c be any real number. Set let c be any real number. Then let us find out the value. F of c is equal to sine of c. Now this is the value of the function, sine function, at the point c. Then you calculate the limit also. Limit of fx as x tends to c, that would be equal to limit extending to c of sine x. Now wherever x is there, write the value c. Now we get here sine c. And what is the value? The value is also sine c. The limit is also equal to sine c. So what is our conclusion? That a c I have taken to be some real number. So when this holds good for some real number, it holds good for all the real numbers. If I had given a particular value, then we say that only at that point it is continuous. Since c is any real general number, any real number, I am using the word any real number, that means that the function is continuous for all the real values of x. So you have to write the conclusion here. Since the value of the function and the limit of the function at a general point c, they are equal to each other. Therefore, the function is continuous for all the real values of x. Now, that means that the function sine x is a continuous function. The same argument holds good for the cos function also. Usually sine function is asked in the examination. If cos function is asked, no, then also the same argument holds good, because even cos function is defined for all the real values of x, and there also the value of cos theta lies between -1 and +1, some fixed quantity between a finite quantity between -1 and +1 here. So the same argument holds good for that also. And you may observe, if you draw the graph of that one, it is a continuous thing. Now let's move on to another problem which again deals with the sine function. Next problem is find all the points of discontinuity. Find here in the previous problem, what did I ask you? Discuss the continuity of the sine function. So sine function was given, we just found out it was a continuous function. Here our problem is to find all the points of discontinuity of the function. The function is defined like this. The function fx is equal to, it is defined in two different ways. First part is sine x divided by x. Under what condition? If x is less than 0. If x is less than 0. The second thing is x plus 1. It's equal to x plus 1 if x is greater than or equal to 0. So here also a particular point is not given, and I am telling you repeatedly, when the function is defined in this particular fashion, less than some value, greater than some value, you have to consider three different cases. See, when the value is x is less than 0 or maybe 1 or 2, whatever number is given there. So in this particular problem, when x takes a negative value, you have to take the function to be in this way and you have to argue whether it is continuous or not. When x takes a value greater than 0, positive value, the function is defined like this and you have to find out whether it is continuous or not. Now at exactly 0, at exactly 0 means you have to, because it is defined for the lower value like this, higher value like this. So when you take the point x equal to 0 exactly, you have to consider both the left hand limit as well as the right hand limit. So we will be discussing the three cases one by one. Now case 1. Case 1, let x be less than 0. Let x be less than 0. Then how is the function defined? That is equal to sine x divided by x. Sine x divided by x. Now here it is a negative number. So I am taking a general value as usual. Let c less than 0 be any real number. See here, you observe x is in the denominator position. X is in the denominator position. So you know the rule that this should not take the value 0 because division by 0 is not defined at all. But here I am taking a value less than 0, any negative number. Now let c less than 0 be any real number. Then what would be f of c equal to? It becomes sine c divided by c. Now let me get the limit also. Limit of fx as x tends to c. The same function, wherever x is there, write the value c. So this becomes the limit, this becomes the value. What do you observe here? Both of them are equal to each other. Therefore you write fx is continuous. Fx is continuous for all x less than 0. That is, for this particular function, when x takes a value less than 0, when x takes a negative values, the function is continuous. Now let me argue for the other extreme case, that is what happens when x is greater than 0. Now let me take the second case. I usually take the extreme cases first. Let x be greater than 0, that is a positive number. Then how is the function defined? That is equal to x plus 1, which is nothing but a polynomial function. Automatically it would be continuous, but the same procedure we adopt here. Let c greater than 0 be any real number. The procedure is same in almost all the problems. When the point is not given, we always take a general real number. Now what would be f of c? This is c plus 1, the value of the function. And again get the limit of the function f of x as x tends to c. Finding the limit also means wherever the variable is there, we write the value. So that would become c plus 1. So the value is c plus 1. The limit is also c plus 1. So our conclusion is the function fx is continuous for all x greater than 0. So when x takes the negative values, it is continuous. When x takes the positive values, it is continuous. Now the question arises, what happens when x is exactly equal to 0? We are asked to find out the points of discontinuity here. So we have verified before 0, for the negative value, after 0 means for the positive value, at exactly x equal to 0. That's the only other case remaining. Now case 3. Case 3, let x be exactly equal to 0. Now here equality is here. So how is the function defined? That is f of x is equal to x plus 1. But we are calculating the value at exactly 0. So put x equal to 0. Therefore, f of 0 equal to 0 plus 1, that is equal to 1. So this is the value of the function at x equal to 0. Now this value of 0 can be approached in two different ways. Through the values less than 0, through the values greater than 0. That means that we have to calculate both the left hand limit as well as the right hand limit. Now let me calculate the left hand limit. Left hand limit means it is limit of fx as x tends to 0 minus, right, the superscript minus. So how is the function defined for this one? This way, that is limit of sine x divided by x as x tends to 0 minus. See, this value is important here. Minus plus we need not worry, because minus shows that it is left hand limit, plus shows that it is the right hand limit, that's all. Now sine x by x as x tends to 0. I hope you remember in first year PUC, in trigonometric limit, this year also I have revised that one. It is sine x by x as x tends to 0. It is a standard trigonometric limit whose value is equal to 1. We have taken that as sine theta by theta as theta tends to 0 will be equal to 1. So it is a standard limit, standard trigonometric limit whose value is equal to 1. Now let me come to the right hand limit. So here the value of the function was 1, the left hand limit also 1. So we cannot say whether it is continuous or not unless we calculate the right hand limit. Now take the right hand limit. Limit of fx as x tends to 0 plus. 0 plus means for the values, through the values more than 0, that is positive values. How is the function defined? It is x plus 1. So limit of x plus 1 as x tends to 0 plus. So put x equal to 0, the value is equal to 1. So what do you observe here? Left hand limit equal to right hand limit. What does it imply? That implies that limit fx as x tends to 0. You need not write plus or minus here. That is equal to 1. That is equal to f of 0. So the value of the function f0 was 1. The limit of the function as x tends to 0 is also equal to 1. So what is our conclusion? The function fx is continuous at x equal to 0. So for the negative values we have seen that it was continuous. For positive values we have seen that it was continuous. At exactly equal to 0 the function is continuous. So what was the question I had asked you? To find the points of discontinuity. There is no point of discontinuity at all. So how do you write the answer? The answer depending upon the way question is asked. Now you have to write therefore there is no point of discontinuity. There is no point of discontinuity. That is how the answer has to be presented. Suppose I had asked you discuss the continuity, then what you should have written? It is a continuous function, because here I would asked about the points of discontinuity, so I wrote the answer like this. If you are asked to examine the continuity, you should have written the answer as it is a continuous function. So this is how the problems have to be tackled. Now let's move on to another problem. The next problem is also it is sort of a standard problem, I can say, because it's a little bit interesting problem. You have to argue logically and get the result here. Here the question is like this: a function fx is determined by like this, x square into sine of 1 by x if x is not equal to 0, and this is equal to 0 if x is equal to 0. A function fx is defined like this. My question is f a continuous function? So I have given you the definition of the function. You have to find out whether it is f a continuous function. So the procedure is same, but the difference in this problem, of course we have worked out such problems, equal to some value, unequal to that one. So when it is less than or greater than, we argue three cases, before and after and at that point. Now in this one, equal and unequal. At x equal to 0, the function is, the value has been given already, it is equal to 0. That means 0 is the value of the function at x equal to 0. Now, we try to find when x is not equal to 0, how is the function defined? It is defined like this. So, when x is not equal to 0, we try to find the limit of the function, because here if you give the value x equal to 0, they have already given the value, no need to calculate here. When x does not take the value 0, it may be negative or positive, we are not given any particular value. When x is 0, it is given. X is not 0, we have to get the limit of the function. Suppose the limit is also equal to 0, because value is already given. If the limit is also equal to 0, the problem is solved. That is, we can come to the conclusion that it is a continuous function. So how do you start with here? Right? No, writing the case 1, case 2 like this. When x is equal to 0, f of x is equal to 0, that is f of 0 is equal to 0. F of 0 equal to 0, that is over. Now, when x is not equal to 0, that is the question here. When x is not equal to 0, let me calculate the limit. As x tends to 0 is equal to limit of x square into sine of 1 by x as x tends to 0. Again, whenever I work out some problem, whether it is algebraic limit or trigonometric limit, we have to refer to the standard limits which are learnt in the first year PUC. That's why usually we revise that in second year PUC also, it's a continuation. Now, look at the right hand side. The function is defined like this whenever x is not equal to 0. How many functions are there? There are two functions here. One is x square, the other one is sine of 1 by x. It's an algebraic function, it's a trigonometric function. Now, according to the algebra of the limits which are learnt in first PUC, see, limit of f into fx into gx can be written as limit of fx into limit of gx. That is, limit of a product is equal to product of the individual limits. So, let me use that fact here. That would be equal to limit of x square, first function, as x tends to 0 into limit of sine of 1 by x as x tends to 0. Now, this is 0. 0 square I can write. It is 0 square because I am just giving the value x equal to 0. See, come to the other one. Suppose I had sine x function, sine of x here. Sine 0 is 0, I could have written 0 there. Now, let me argue here. Now, the function, the term is sine of 1 by x. How is x tending here? X is tending to 0. So, here as x tends to 0, I am having the term 1 by x. How does it tend? It tends to infinity, because see, when 0 comes in the denominator position, we denote it as infinity. So many times I have told you that infinity is not a number. Whenever 0 comes here, we denote it by infinity. We mean that it's a very big quantity, a very huge quantity. So, as x tends to 0, 1 by x tends to, I am saying, it is moving towards a higher and higher number, higher quantity, where we are moving towards that. Now, again, as in the earlier problem I told you, the function sin x is defined for all the real values of x. However big x may be, however x small may be. It may be small or a big quantity, the function sine is defined. So, as x tends to 0, 1 by x tends to infinity. Sine of some number, I can say sine of 1 crore, let me take 1 crore degrees. Then, and whatever may be the value of x here, whatever may be the, for any theta, for any angle theta minus 1 less than or equal to sin theta less than or equal to plus 1. It's a finite quantity always, irrespective of the value of x we are giving. For sin function, same thing holds true for cos function also. So sin theta and cos theta, their values always lie between minus 1 and plus 1. If you know the exact value of theta, we can get the exact value. Otherwise, for any value of theta, however big or however small that may be, sin theta always lies between minus 1 and plus 1. What do you mean by that one? It is always a finite quantity. So, limit of this one is 0 square. This is a finite quantity. It is a finite quantity. Okay. Now here, if sin x we had, we could have directly written sin 0, 0. It is sin of 1 by x. So, as x tends to 0, 1 by x tends to infinity. The value becomes bigger and bigger. So, whatever may be the value of 1 by x, value of sin of 1 by x will always be a finite quantity. So, 0 because the value of sin theta for any theta lies between minus 1 and plus 1. It cannot go beyond these two values. It cannot be less than minus 1. It cannot be greater than plus 1. Therefore, 0 into any finite quantity is 0. So, the limit of the function is 0. The value of the function is 0. So, what is our conclusion? It is continuous. So, when x equal to 0, it is 0. When x is not equal to 0, whatever may be the value of x here, when you get the limit of that one, it would be equal to 0. So, generally we can come to the conclusion that it is a continuous function. Now, this is how we have to argue. Now, another problem again which involves the trigonometric function. Now, this problem just now I worked out. It is some interesting problem I can say, and which was asked in the earlier examination also. Now, let me consider again the question in the next problem is examine the continuity of the function. So, you have to find out whether it is continuous or not. Now, examine the continuity of the function given by fx equal to sin x minus cos x if x is not equal to 0, and this is equal to minus 1 if x is equal to 0. So, two possibilities are given. When x takes the exact value of 0, the value of the function is given to be minus 1. So, value is known already. When x is not equal to 0, not equal to 0 means, see, when less than or greater than signs are used, we have to discuss before for negative positive values separately. It is not equal to 0, equal to 0. There are only two possibilities. So, when x is not equal to 0, we try to find the limit of the function. Now, when x is equal to 0, f of x is minus 1, that is f of 0 is equal to minus 1. So, the value is known to us. Now, we have to get the limit. Now, write when x is not equal to 0, then the question arises, limit of fx as x tends to 0. How is a function defined for all x not equal to 0? This is how it is defined. Limit of sin x minus cos x as x tends to 0. Now, simply you write the value x as 0 wherever x is there. So, this would be equal to sin 0 minus cos 0. As you know, sin 0 is 0, cos 0 is 1. Both of them are standard values. This is equal to minus 1. So, what do you get here? Limit of fx as x tends to 0 is equal to 1. And what is the value of the function? That is also equal to 0. So, the limit of the function fx as x tends to 0 is equal to minus 1. The value of the function at x equal to 0 is also equal to minus 1. So, in this case also we observe that both the limit as well as the value of the function are equal to each other. That means that it is continuous at that particular point 0. So, here are only two cases, x equal to 0, not equal to 0 means any point not equal to 0, the function becomes a continuous. So, generally we can come to the conclusion that it is a continuous function. So, suppose the function involves some standard limits here, you have to remember it may be algebraic, trigonometric, exponential, logarithmic function, whatever may be that one. Since you are familiar with the standard limits here, you can use that one. If it is some polynomial function directly, we can get the result. So, in all these sessions that we have worked out some problems on continuity under the same chapter, we had considered some problems where the point was given, or if the point is not given also, we take a general point and argue. In the coming session, the next session, I am going to work out some problem where it would be given that the function is continuous, but there would be an unknown quantity which has to be, whose value you have to calculate taking the function to be continuous. So, when the function is continuous according to the definition, the limit of the function and the value of the function, they have to be equal to each other. So, equating those two quantities, when you equate, the unknown quantity comes on any one side of the equation. So, it can be a simple equation or a quadratic equation, depending upon that we are going to find the value of that one. That is usually asked for a 4-mark question in all the earlier examinations. Now, I will take up that in the coming session. Thank you.